Hello, I'm Jim Adams, and I would like to tell you about the bounding case radiation environment for short crewed missions. As you may know, NASA is planning to return astronauts to the moon in a new program called the Artemis program. The program consists of putting two spacecraft at the moon. One is the Lunar Gateway spacecraft, which will be in orbit of the moon. And the second one is the lunar lander. The exploration crew will be on the Lunar Gateway, and they will enter the lunar lander and descend to the lunar surface for missions lasting up to 10 days. Now, when NASA designs their crewed missions, they require their contractors to include in the design sufficient shielding to provide radiation protection for the crew. In order for the contractors to do this, they need to be told the radiation environment outside the vehicle. So NASA provides them with a design reference environment for this purpose. NASA has developed a design reference environment for deep space missions. I was part of the committee that developed that environment. And I can tell you that what we had in mind were missions lasting a year or more in duration. So that environment is appropriate for the Lunar Gateway. But NASA was concerned that it would result in over-design if used for the lunar lander because of its short mission. And so we were asked to develop a spatial design reference environment for short crewed missions lasting no more than 10 days. And that's the subject of this talk. The approach we took is a data-driven approach. We used proton and helium spectra from the GOES satellite to create a large sample of simulated missions. We removed from that sample the missions that were at background and used the remaining missions to create cumulative distributions for each of the GOES energy channels. Now, to find the bounding case spectrum, the user needs to specify the confidence level that he wishes for each of the bounding case fluxes or bounding case fluences. And we need to correct his confidence level for the background and then use it to index into the cumulative distributions we've constructed from the simulated missions. The result of those calculations are spectra like the ones shown here. The one on the left is the bounding case spectrum for protons. It's a differential fluence spectrum. And the bounding case spectrum for helium is on the right. These spectra were created assuming that the user specified his mission would occur when the sunspot number was greater than 150. He wanted a 95% confidence level, and his mission lasted for 9 days. Now, let me go into more detail about how we did this. The databases we used are shown here. The proton database consists of 30-minute averaged flux measurements from the GOES NOAA satellites. So there's a flux measurement every 30 minutes from 1986 to 2016. We identified and removed the bad data in the GOES data set, and we filled the gaps, and then we subtracted the background from the GOES data. The helium database we used is the one ESA developed as part of the SEPM project. It consists of 5-minute average fluxes. And so there is a 5-minute flux measurement every 5 minutes from 1974 to 2015. Again, the bad data were removed, the gaps were filled, and the background was subtracted. The method that we used is to construct cumulative distributions for each of the energy channels. The distributions are constructed from mission integrated fluences that are above background. These distributions are evaluated at the user specified confidence level to find the bounding case flux for each of the energy channels. The user can be confident then that at his specified level, these bounding case fluxes will not be exceeded during his mission. To do this, we needed to consider the variation in solar activity because that affects the frequency with which solar energetic particle events will elevate the radiation environment at Earth. What we found was that if we use the sunspot number as an indication of the level of solar activity, then we could divide the sunspot number range into 4 groups, the 4 groups shown here, and within each of these groups, the probability that the radiation environment would be elevated at Earth was about the same. So the user needs to specify in which of these sunspot groups his mission will fall. Since the missions are in the future, he needs a prediction of the sunspot number, and those predictions can be obtained either from Vincent et al. Or from the NOAA predictions at the website shown here. For constructing simulated missions, we constructed these missions by dividing the database into mission length intervals comprised of the nearest whole number of flux measurements. The fluxes were integrated over each mission to obtain mission integrated fluences for each proton and helium channel. These steps were repeated, offsetting the starting points by 1 measurement in order to obtain as many simulated missions as possible in these databases. The process continued then until the next round would result in repeating the first set of simulated missions that we had calculated. So the result is a very large number. The result is a very large databases of proton and helium fluences for each of the energy channels for these simulated missions. Now, next we needed to consider the active time ratio. This is the fraction of time that the radiation environment at Earth is above background. And we calculated this using this large database of simulated missions. So we calculated the fraction of all emissions that were above background. And we did this for every possible emission specification. So there's an active time ratio for each element, each energy channel, each user specified mission length, and each sunspot group. This is an example of a cumulative distribution that results from this effort. The cumulative distribution shown here is for a 5-day mission with a sunspot number greater than 150. And then the red dot shown here is an evaluation of the bounding case fluence for a confidence level of 95% specified by the user. So that's applied to the horizontal axis, and the vertical axis then is applied to the vertical axis, and the horizontal axis then gives the bounding case fluence. So to find this bounding case fluence, we need to correct the confidence level given by the user. And the method we use is shown here. We need to consider that we need to use the active time ratio, and the quantity C is the confidence level specified by the user in percent. And the equation here corrects that to obtain C prime, which is what we use to index into the cumulative distributions. If C prime is greater than 1, it means that the bounding case fluence for the mission is actually at the background level. Otherwise, C prime is used to evaluate the cumulative distribution for each of the energy channels in order to obtain the bounding case fluxes. Now, the GOES energy channels are quite broad, so even when all of the energy channels are above background, as is the case with the proton spectrum shown here, you still need to have a better definition to provide the spacecraft contractors. And so we needed to fit a spectrum through these 6 data points. These broad energy channels need to be carefully considered, one needs to use an effective energy for each of the energy channels if you're going to fit a differential spectrum or spectral form. And so we used the Sandberg effective energies from the NOAA CEPM project. And we also took another approach. We energy integrated the fluences over each of the energy channels and used the integral form of the spectral representations in order to fit them to the spectrum. Both approaches produced very similar results. The spectral forms we considered were ones which have been shown to fit many solar energetic particle spectra. We used the power law, the Weibull function, and the band function. And if two or more of these could be fit to the data, we then chose the one that gave the lowest chi-square fit. So in summary, we have developed a model that calculates the differential fluence spectra for solar energetic proton and helium nuclei for missions less than or equal to 10 days. The model requires the user to tell us in which sunspot number group his mission will occur, what the mission duration is, and what confidence level he desires. And with those data, this model will then calculate the bounding case spectrum for each of the elements. But to get the design reference environment, one needs to add to that bounding case spectrum the galactic cosmic ray background. So let me leave you with the list of references that I mentioned in the talk. Thank you.